how we use computers in business today. Now the problem is that so do our bosses and our stakeholders. They see the same advertisements. And so do you ever get asked, how come we can't do that? Or when will we be able to use AI? This is actually a true story. One of my stakeholders recently called me up, and this person was having a problem with WebEx, where one of the participants in WebEx, they couldn't be heard on the call. Actually, let me just take a pause there for a second. Isn't it great to be in IT? On one hand, if your business stakeholder needs help doing a multi-million-dollar program to transform and support their billion-dollar business, then call Bailey in IT. Awesome. However, if one guy can't be heard on WebEx, you can't make WebEx work, we'll call Bailey in IT. That's our job, right? That's what we do in IT. Well, anyways, we called this guy in IT, or we called this guy that couldn't be heard on the phone. He said, hey, what's going on? This was a very important call. People on the call couldn't hear you. What's going on? He goes, oh, I'm really sorry about that. I was on vacation. I was on the beach somewhere, and a very poor signal. Maybe it was in Cancun, right? So we went back and I went to talk to the stakeholder and say, hey, it wasn't actually a problem with WebEx. It wasn't a problem with the technology. The guy just had a poor signal. He was on a beach somewhere. And my stakeholder said, can't you just do some of that AI stuff to fix the problem? And so the reality is people, our stakeholders, they hear the hype. They think AI is like some kind of magic dust that you can sprinkle on your hardest problems and make the problem go away, right? Now the reality is AI is actually very powerful technology and it can solve some really great problems. But for other problems, the result might be not as good as anticipated. So what I want to do today is just kind of talk about what is AI, where does it make sense to use it, share with you a framework of what technology to use when, and then to also share some examples of where we've successfully used AI in Cisco IT. Some cases where it's worked great, and other cases where it hasn't worked so well. So first things first, let's go into what exactly is AI, or artificial intelligence. You might hear the term ML quite a bit, machine learning. Or more recently now, a lot of people are starting to refer to DL, or deep learning. So let's talk about what exactly these technologies are, and how do they work. So the first thing to really help you understand how these technologies work is to compare it to traditional computer programming. In traditional computer programming, the human being actually creates the steps for the computer to follow to solve the problem. And the human being must actually have a deep understanding of the rules. So as an example, very simple computer program might be to try to identify a shape. If the number of corners is 0, then the shape is a circle. If the number of corners is 3, then the shape is a triangle. If the number of corners is 4, then it's a square. Traditional computer programs work the best when you can break the problem into very discrete steps and the rules are very well defined. But where computer programs might start to struggle, if you're trying to do something like identify a flower. Sure, you could probably write a program that would work on one flower. If the color is red and the size of the flower is less than 6, then the flower is a rose. The problem is that flowers are products of nature. There's a lot of variability in flowers. And if you tested this program against many flowers, it would probably fail. The reason why is, well, roses come in all shapes and colors. So how would you actually write a computer program to work on this set of data? It'd be something like this. The color is red, or the color is yellow, or orange, or pink, or white, or lavender, or purple. There's too much variability. You can't write all those rules. That's where traditional computer programs fail. Now, this would actually be a fantastic problem for machine learning to solve. And so, why? Why is machine learning for this problem better for this problem instead of traditional computer programming? So let's understand the difference. As I said, in traditional computer programming, it's human beings that create the steps for the computer to follow. In machine learning, human beings actually choose the data. We find the data that says, these are all roses, but it's the computer that figures out how to solve that problem. So how does it do that? Let's go into it. There are 4 steps for the first wave of machine learning. The first is to really have good data available. And this is actually the hardest part of the problem. When I say good data available, what I mean is that the data has to be labeled. It's no use to have a lot of data about flowers that are not labeled. But what you need to have is, this data is for a rose, this data is for a tulip, this data is for a daisy, so on and so forth. So all your data actually has to be labeled. And this is actually the hardest part of machine learning. And companies that don't have labeled data, most of the time they'll just outsource it or crowdsource it. That's the first step. You have to have good, not just a good quantity of data, but a good quality of data that's already been labeled. The next step is something we call feature engineering. And this is about choosing those right pieces of data that's going to solve your problem. So if you think about it, when I talked about we had data for a rose, this type of data might actually be in your data set. You have things like the petal color, the sepal shape, the leaf cluster, the sepal length, the leaf color, and the presence of thorns. Not all of this data is actually useful to our problem. So feature engineering is about choosing those bits of data that really will help you solve the problem. And in the case of rose identification, it turns out that sepal shape, which is the shape of the reproductive organs on the rose itself, leaf cluster, which is the amount of leaves on the rose, most roses actually have a leaf cluster of 5, and the presence of thorns is much more useful to solving this problem than, say, petal color, sepal length, and leaf color. If you think about it, most leaves are green. But if you train the computer to say, when the leaf is green, it's a rose, it's going to get confused. So feature engineering is about picking the right pieces of data that will help you solve your problem. A feature is an attribute that is useful or meaningful to your problem. Now, it's called engineering because in many cases, you're going to have to do some software development to really solve this. In our use case here, it's very simple. You just pick the right pieces of data. In other use cases, you might actually have to take the data, transform it another step for it to be more strongly connected to the problem you're trying to solve. I'll talk more about this when we get into the WebEx example. All right, so you have your data, you've picked your the features. Now the next step is to actually choose your machine learning algorithm. There's quite a few of them. So this was a list published by Richard Brownlee in 2013. And it goes over the most basic concepts of machine learning and all of the different algorithms that were kind of created off of those basic concepts. There's a lot more now. But basically what you're trying to do is to select an algorithm that when you feed it an input, it's going to create an output that will help you solve the problem. Let me show you what I mean. Let's say we pick one, and we feed it the data that we have, and the output kind of looks like this. This actually doesn't really help us with anything, because all the data is still kind of mixed together. But if we chose a different algorithm, same data, the output might look like this. Now we're getting somewhere. The data is starting to kind of spread itself out into definite clusters. And with this, we can actually start to make predictions. So to put it all together, we took our features, we trained up a model, we chose our algorithm. Now let's actually use it. We're going to feed it some new data. Here's a data set for this thing, for this flower. We run it through the algorithm. It shows up here. Because of this, computer can say, it's a rose. This is the first wave of machine learning. And the one thing to keep in mind, though, is that even though this is almost nearly ideal situation where the data is so clearly differentiated, you're still going to have areas with errors. If you look at it, there's definite overlap with the algorithm and some of where the data shows up. So these are areas where the computer might make a mistake in this prediction. If you fed it input and it showed up in one of these circled areas, the computer can make a wrong prediction. So, you're probably thinking by now, really, this doesn't seem like learning at all. This seems more like statistical or statistical or mathematical analysis. That's actually kind of true for the first wave of learning. I'm going to actually talk about, we're actually on to the next wave of machine learning now, which is called deep learning. And in deep learning, we're going to use the computer to try to mimic the way that the human brain works. And so what deep learning does is it uses a neural network to try to solve the problems. Instead of a mathematical formula or a statistical formula, it's going to try to mimic the brain to solve a problem. Now, deep learning is actually fairly complex. So I'm going to greatly simplify it. Okay, so this is not going to be something that's going to pass, a deep artificial intelligence researcher, but at a higher level, it's just kind of explaining how deep learning works and how neural networks work. So let's say that we wanted to train a neural network to identify good pasta. And in our data set, we talked about features, which are data that is relevant to the problem. So to identify good pasta, the things that are relevant to for the problem is the amount of pasta that we have, the amount of salt, the amount of olive oil, and the amount of water. And so what we're going to do now is we're going to build up this neural network, and each of these things becomes what's known as a node in our neural network. We take our first data set, the very first one, and we say, okay, this is good data. Again, remember that problem about labeling the data, right? So human beings have to label the data. I am telling you, computer, this is good pasta, data set number one. Then what it's going to do, it's going to run it through the neural network. It says, okay, my human master says this is good pasta. The weights and the nodes are telling me otherwise. The computer's saying, this to me feels like it's too salty. Too much salt. So what I'm going to do now is the computer is going to go and iterate on the weights and the nodes until it comes up with a result that matches what we told it, which is good pasta. So it's going to adjust the weight in the salt node downwards, and it's going to do that over and over again, 10,000 times or more. It's going to keep retesting and retesting, self-adjusting the weights in the neural network until it finally says, you know what? This seems to match what the data said I got. This seems like it's good pasta, and that's what the human being said, that this is good pasta. And that's just for data set number one. So now, if you multiply that by the amount of data that you have, and typically to build a neural network, you might need 50,000 or more data sets. You can quickly see the amount of intensive calculations that are needed. So one thing to take away from deep learning is that you need a lot of computer power to actually build this neural network. And like before, now you've built your neural network and ready to use it. And so what you're going to do is feed it new test data, and depending on the path that it takes, the computer will be able to tell whether or not it's good pasta or bad pasta. I didn't get a chance to have lunch today, so I don't know if we ran the cafeteria's food through here, if it was identified as good or bad. Maybe that's a test for us later, a little bit later on. But that's how neural networks work. You train it, you build up the neural network, and then you're able to use it to test. Now, a real-life use case is actually for facial recognition. This is a very, very powerful technology, well-suited for facial recognition. And so what happens is, same type of thing, you train it, it starts to learn, and then what happens is different paths through the neural network will come out as basically identified as different people. So you take one path, it's one person. You take another path, it's the second person. You take a third path, it's the third person. And so you can see the difference between kind of machine learning and deep learning then. Machine learning, it's the mathematical formula, it's the statistical algorithm that determines the output. In deep learning, it's the weights in the nodes and the path through the neural network that determine the output. But I mentioned that in deep learning, we try to train the program to learn like a human being learns. And that's both good and bad. One of the bad things about the way that human brains work is that once you see something, it's hard to unsee it. Right? Guillermo Diaz actually talked about, as IT leaders, our job is to learn, unlearn, and relearn. That's actually easier for a human being to do it than it is for a computer to do it. So if you've trained up your neural network and you have a bad piece of data in there, it's very difficult to remove those nodes. And the reason why is because the nodes are all highly interconnected. You can't take out one node without impacting all the other nodes around it. So if you have a path in the neural network, you can't take it out. And as a real example of where this error shows up, I have an example of that. So a tale of two people. You've all met Guillermo Diaz. He's our CIO. And you know Bailey Zito. So Guillermo Diaz, he's no longer here, so I was going to make some joke about being powerful and handsome, but he's not here, so I don't have to say that anymore, right? And Bailey Zito, right? Not so powerful, not so handsome, computer. Two very different people. And, you know, we're friends on Facebook, and Facebook has facial recognition, and they're using deep learning and neural networks. No surprise. It's the best technology for facial recognition. Once upon a time, someone accidentally tagged Guillermo Diaz as Bailey Zito. And as I said, once the computer learns something, it's very hard to unlearn something using a neural network. And so what has happened since then is that whenever my boss posts a picture on Facebook, it tags it as Bailey. This has actually caused me a lot of grief at my household, by the way. Because my wife says, who is Hema Diaz and why was she with you in Hawaii? And unfortunately, like I said, there's just no easy way to, sure you can untag this one picture. In theory, if you fix it enough times, the computer could relearn it. But for now, whenever my boss posts, it's Bailey. Whether it's in his own feed, I think I'm looking pretty good here. And probably what makes it worse is it's not just his Facebook. You know, we have the same circle of friends and coworkers, so when they post, my friend Marisa, same thing. Marisa's with Guillermo, and there it is with Bailey Zito. So you can see that there is a drawback to neural networks, which is once it's trained up, it's actually hard to fix it, which is why it's critically important that you be careful with your training data. Because it's hard to fix, you have to be critically careful of your training data. And that includes making sure that you don't have bias in your training data. There's a lot of issues right now where the people who have been working on neural networks are not diverse enough. So you actually get one view of the world that was used to train a lot of these neural networks, and therefore the output is not what is anticipated. My friends Caddy Colson and Maria Medrano, thank you, sorry. Maria and Caddy will actually be talking about bias tomorrow. So it's a good topic to connect with what we're learning today. Okay, so then what is AI? We talked about machine learning, we talked about deep learning. What is AI then? And simply put, AI is when computers to perform a human task. Actually, let me just stop and say, if you use this definition, then that whole AI-powered toilet thing goes to a whole nother level, right? But AI is when a computer can perform a human task. And a best example that we're all familiar with AI is self-driving car. That's when a computer can do a human task of driving the car. And so what is it then? Well, simply put, AI is just an umbrella technology. AI uses everything we've already talked about to perform that task. So yes, AI does use machine learning. It uses data from the sensors and an algorithm to predict the action of what's coming next. AI does indeed use deep learning, right? It uses deep learning to identify objects on the street. Is that another car? Is that a person? That type of thing. And sure enough, AI, of course, uses traditional programming. It doesn't make sense to try to use machine learning or deep learning to do simple rules. Traditional programming works best when the rules are concrete. Red means stop, green means go. Just use traditional programming on that. Don't bother with DL or ML or whatever. All right, now that you understand what these technologies are, let's talk about when does it work, when does it not work, and I'll share with you some examples that we've tried at Cisco. So I'd like to introduce this framework, a very simple framework, that will help you determine when you attempt to use these technologies. The first on the x-axis is very simple, data quantity. Very simply, how much data do you have? On the y-axis is something called the relevant features availability. To remember, if I talked about it, I said features are attributes that are useful or meaningful to your problem. So it's not just the number of data fields you have, but are any of them relevant to the problem? Remember the rows where I talked about, hey, even though we have 6 or 7 different fields, only 3 of them matter, right? So this is the amount of fields that actually matter to the problem. So if you actually use this 2x2, and if you have a low data quantity and a low amount of relevant features, then the results are not guaranteed. There's not enough data to actually completely train the computer, and you don't have enough features for it to kind of pick up on things. In this case, it might be better just to use traditional computer program. If you have a low quantity of data, but a high number of relevant features, then that's a candidate for machine learning. Because those important features can help you pick an algorithm that's really going to match up nicely to help you kind of come to that outcome you're looking for. Likewise, if you have a large amount of data, but a low amount of relevant features, then that's a candidate for deep learning. The reason is, in many times, if you have enough data, the computer can spot a pattern that you may not be able to. So you're looking at the data, it's like, I don't see anything in here that actually seems like a relevant feature. But if you have enough data, maybe the computer can find something. Last but not least, if you have both, then both of them actually could be good for machine or deep learning. And so your question is, well, which one should I use then? And the answer is it depends. Deep learning is typically going to be better from an accuracy perspective, but as I said, it's very computationally expensive. So do you have a large amount of servers to dedicate to deep learning? Or if the need is not that high for super duper high accuracy, and you just need a good enough accuracy, then machine learning is probably your best bet because it's cheaper and faster. So let me share a couple of examples where we have used machine learning or deep learning and kind of share whether it worked or not. The first example is Cisco Answers Machine. So we get a lot of questions from you, our customers, and our partners. And we actually have a whole team dedicated to answering basic product questions. We get about 300,000 cases a year. This is questions that the seller didn't answer, so it's been escalated to another team. And about 40% of those questions are basic product questions. So we tried to build something to kind of help with this let's just see if we can answer basic questions about our products. Now, we do have a lot of data available. We have tons of documents, millions of documents. And the problem is that if you think about the documents that we have, product guide, spec sheet, installation guide, architecture guide, in addition to Cisco 401ks, all the financial stuff, information about our company, all those things, a lot of them actually have the same phrases. In fact, if you were to search on catalyst, switch, port, you probably get 90% of those same documents back, right? Because those are common words in Cisco language, and they show up everywhere. And so what we do is we use machine learning to try to figure out what kind of document this is. So we run it through this thing called LDA, our algorithm. And what it's able to do is actually kind of start to cluster what type of document the computer thinks it is. Is this more of a product type of document, or is it more of a corporate information type of document? Now that we've kind of separated out our documents, when a customer asks, how many ports does the Catalyst 9300 have? We know that that seems like a question that should come from the product specs area. We're able to pull the right answer from the right area and answer that the Catalyst 9300 has anywhere from 24 to 48 ports. So this is one example where we use machine learning. And the reason it works is because we have lots of data, those million pieces of documents. But more importantly, we have lots of relevant data. We have the actual document itself. So in that document, there's context about what type of document this is. So there's a high number of relevant features. The next example I'd like to share with you is document confidentiality classification. So in fact, I think you heard from both John Stewart and Jason also talk about today, we actually have an information security policy at Cisco. So what's supposed to happen is you as an employee, you're supposed to take a document as you create your content, you're supposed to mark it with the appropriate security classification. This presentation is Cisco Public. You can see it right on the bottom. Now, at the end of the day, we're all human beings. Every company, we're all human beings. So what happens? Instead of trying to find a template, what I do, and I think most people do, they find someone else's presentation, erase all the slides, and then build a new deck, right? That's human nature. But what happens is that most of the time, people are not going to change the security classification. So what ends up happening is if you look in our repositories, pictures from the holiday party, Cisco restricted or Cisco highly confidential. You know, the menu for the lunch, Cisco restricted, right? So there's a lot of misclassified documents in our repositories. And so we wanted to see if we can use machine learning to help fix this problem. Can the machine do a better job of identifying documents than a human being can? Well, actually the answer is no. Human beings can always do a better job, but because they're lazy, can the machine do it for us? That was the question. Well, unfortunately, we failed. We attempted it, we tried to use machine learning, we had a very high error rate, 35% incorrect. And the reason why it didn't work was ultimately there was a lack of relevant features. You're probably thinking, hold on a second, man. In the last use case, you said there were a high number of relevant features because you had the whole document. And now, I'm saying there's a low number of relevant features, but you still had the whole document. How can that be? Well, when it comes to trying to identify the security policy, you need information that's outside of the document. And that's what we didn't have. We didn't have a larger number of relevant features because the relevant features are features that are outside the document. For example, if you have a document that has your earnings numbers, before it's announced, it's restricted. But after you announce it, it's public. Right? That is the main feature you need, the date at which the information moves from being restricted to public. But that wasn't in the document itself. So this use case failed because we did not have enough relevant features. Make sense? Okay. All right, and then you actually saw this in the demo yesterday from Sonori. Noise detection in WebEx and Cisco TP units. And so we all have been on WebEx calls. I spend a lot of time on WebEx. I think it's great. It allows me to work anywhere. But I don't think we like it when there's too much noise on the line, right? We've all been there. Great call, dogs barking, sirens going, or my personal favorite, what I call the Darth Vader. Right? This is when the headset's too close to the mouth. Right? The Darth Vader. So the question is, and what our business unit tried to do was, can they detect these type of noises to automatically mute them? And so in fact, Sonori talked about this yesterday, right? He said his team told them, guess what? Your voice and a dog's bark look almost exactly the same on a traditional audiogram. And it's true, if you look at it, those two things look very similar. In fact, the industry has tried to use standard audiographs for many years. Like the early speech-to-text recognition was attempted to be done using this technology. It's never gone very far because they're kind of the same. Now, if you remember, I said one of the key parts of machine learning is something called feature engineering. And I said it's engineering because sometimes you have to transform the data one step more to actually solve the problem. So that's exactly what I mean here. They had to take the audiograph and transform it into something else. In this case, they moved it from a traditional audiogram to a mil spectrogram. You can see the differences start to become much more apparent using this representation of the data. And so once you have it in this format, then you can apply deep learning to it. And you can go through that same process I talked about already. You get the data, you start to build your neural network by looking at the patterns, build out your neural network, and then you're able to determine, hey, there's an 85% chance that the noise I just heard was a voice. And that's how this team, Sonori's team, has been able to use deep learning to identify unwanted noises and automatically mute. And the reason why this works is there's lots of data available for the common noise to be detected. We can find lots of samples of dogs barking or sirens going. And the noise data itself can be consistently transformed into a format that's good for deep learning. So this is a great example of deep learning and how at Cisco we've been successfully being able to use it to improve your WebEx experience. So we spent some time today talking about, what is AI, what are the different technologies involved, and some examples of where it made sense, how did we use it. So a couple of key takeaways. First, be aware of the high data preparation effort. I recently had my house painted. It took 3 times longer for them to prep for painting than it was to paint. Machine learning, deep learning, same thing. It's going to take you longer to prepare your data than it is to actually to run the data, to actually use those algorithms or deep learning. You have to be aware of any accuracy limits of these systems. I shared that for machine learning, errors occur when the clusters overlap. And then for deep learning, errors occur when you've trained it incorrectly. It's hard to fix it after the fact. You have to be aware that none of these systems, they can be quite good, but they're not perfect. So that means that you also have to be aware of the high cost of an error. If the computer kind of misidentifies a flower, so what? No big deal. But if the computer recommends the wrong prescription drug, that can be fatal. So inherently, both of these things have some limits to their accuracy. You don't want to use it for the wrong type of problem. And last but not least, both of these technologies, or all of these technologies, can make a prediction, but in many cases they can't tell you why. You can run the data through and you can say, oh, this engine's about to fail. But it can't tell you why it thinks the engine's about to fail. So that's a key thing to know when you're considering the use of these technologies. So the key takeaways are AI and ML and DL is not just a technology, but it's really a paradigm shift. We're going to completely change how computers can be used to solve problems. The capabilities will only get better due to increasing computer power. The server we use for machine learning is a Cisco product, the Cisco C480ML. It's a server meant just for machine learning. It has 640 cores in there. What happens when that same server can hold 6,000 cores or 60,000 cores? The size of your neural network can become much larger, and you might be able to see much more insight from that increasing computer power. Match the method to the problem. Sometimes traditional programming is the simplest and fastest way. So even though these technologies are kind of neat and sexy, sometimes don't forget that the easiest way might be just to solve it the old way. And last but not least, the framing and the scoping of these problems still require us, the human beings. Speaking of the human beings, Joseph Bradley, a peer of mine, will be coming here tomorrow to talk about the social and ethical implications of AI. He's a great speaker. Highly encourage you to attend his session as well. So, last but not least, we have learned about the basic AI and ML technologies. Now kind of understand basically how they work, what are some of the limitations. It's your job as IT professionals to separate the reality from the fiction, because you have to advise your stakeholders. So I encourage you to keep track of this technology, experiment with it, use it for problems that make sense, because ultimately you have to ensure that you're there to support the business. So these need to be, you have to have a very good understanding of these technologies, because they will fundamentally change what IT is doing. So going back to my first question, do I think AI is going to choose the next sports star? Is it going to create award-winning music or create world-class recipes? Not there yet, but perhaps soon. Thank you very much. It's been great talking to you.